Welcome to EDU World Space.
We'll be using superposition and Coulomb's law to determine the electric field on a point P along the axis of a charged half ring. And we'll assume that that charge is distributed uniformly over the upper half of a ring that lies in the xy plane. So we're going to actually use Coulomb's law and integrate little tiny chunks of electric field vectors over the length of the ring. So the idea is we are going to break up the half ring of source into little tiny chunks of charge dq. The other thing that I'm going to do that looks a little bit strange is, instead of being an inverse squared law with a direction expressed with a unit vector, we're going to put the full separation vector r upstairs, and then we'll have r cubed down below. So that term with the r's in it is really the same as a unit vector r over r squared. But it'll make the calculation a little bit easier recasting this. Okay, so now we just need to fill in some of the pieces. There are many ways to write the dq, but if it is a linear charge density, dq is the linear charge density times a one-dimensional differential. Here, because it is an arc, we're going to use ds along the arc. So I've identified a little source point inside of that ring, and ds is the length of the arc at that point. So we'll give the circle a radius r, and ds is just r d theta, with d theta going, of course, from 0 to pi as we integrate all the way around the half circle. Okay, so that's one thing down. And let's just expand dq out, is lambda times r d theta. So a hint that we'll have to integrate over the angle from 0 to pi, going halfway around. All right, now to work on the separation vector. R is actually the difference between the observation vector coordinates minus the source point coordinates. And our observation point is lying along the z. Sort of depends how you set it up. The source point is lying in a circle in the xy plane, so has coordinates r cosine theta, r sine theta, and no z. There we go. So the observation minus the source. So we have the coordinates there. And our r vector turns out to be minus r cosine theta, r sine theta, negative, and a positive z. Its magnitude can be worked out with Pythagorean theorem. We get a cosine squared plus sine squared, and the negative in front of r cancels. And that's kind of nice. I don't see our integration variable within that quantity, which is nice. Okay, so now we use superposition to integrate all the little source points. So we're really integrating contributions over the source points. So if we had discrete point charges, we would just be adding discrete point charge formulas, but we're kind of using the theta variable to do our addition for us. So the electric field comes out from that integral. And let's see, we have k lambda and 4 pi epsilon naught as a constant. Also notice that 1 over r cubed is coming out as well. And that is because we are not, the integral variable does not appear in there at all. Okay, so really the main thing that shows up is the r vector times r d theta, and we can clean that up a little bit with theta going from 0 to pi. Okay, so we're going to have to do 3 coordinate integrals, and let me break those up. Let me see, the big R comes out. Yeah, the big R comes out. For the x coordinate, we have another factor of r from the deal with the cosine theta. And then we're left with the integral of minus cosine theta d theta from 0 to pi. And notice that that will just give us minus sine of theta from 0 to pi, which is 0. And not too surprisingly, the x component of the electric field vanishes. We could have almost guessed that from the symmetry of the problem, that there's a positive source point on the positive x-axis balanced with one on the opposite side. The y electric field is not going to do that, though. It'll be everything out in front. Yeah, with a 4 pi epsilon naught and the crazy business in the r cubed in the denominator. But now we have the integral of minus sine of theta from 0 to pi d theta. And that turns out to give us cosine theta from 0 to pi, which is minus 1, or minus 2. And that makes sense that this is negative, because the if we assume a positive line charge, its electric field will point down along negative y. So yeah, the EY is negative, and we'll cancel a 2 from the denominator. Okay. And finally, the z component is probably the easiest, because we see that it does not involve theta at all. So we have k lambda r z and then r squared plus z squared to the 3 halves, and then the integral of d theta from 0 to pi, which, yes, no special magic needed to solve for that. That simply gives pi. So we can cancel the pi from numerator to denominator. And we get a fairly simple answer. So not surprisingly, that electric field component turns out to be positive, as long as you're in the positive Z regime. That is, the ring has an electric field that points away from the center if it is positively charged, and towards the center if negatively charged.